How many were at the Perth conference in 2003? Yay! Malcolm tells me that this talk is an elaboration and an update from one that he gave there. Malcolm Tredinnick has been working on Linux since 1993 and accidentally submitted his first patch in 1996. Apparently it's all been downhill since then, as he's worked with Python and C and developer tools and mucking around with makefiles and doing translation management accessibility. He has written code that talks to banks and stock exchanges. He has worked on some reasonably large websites. And one day he hopes to grow up and work out a niche to focus on, but that probably won't happen soon. Can everyone give a warm welcome to Malcolm Tredinnick talking on what is a tiny Linux installation?
Oh, thank you. I thought we said you wouldn't read out the whole biography.
It was too good.
So you lied, okay. All right, I'm me. This is just in case you're interested in how to stalk me online. Stalking me offline, not cool, but online, okay. How did I get here? Like, I'm not a kernel hacker. I'm barely a user space hacker. But I break things and I try and work out why they break, not always in that order. Sometimes I'm just interested in what's going on. But I do have a lot of experiences having started with Linux as a university student, primarily because I was poor and it was free. Things would break and I didn't necessarily have internet connection to work out how to fix them, so there'd be a bit of poking around. So I've tended to sort of grow up over the last 20 years with this idea that, you know, pretty much anything I can work out with enough willpower and curiosity. I'm not an embedded hardware guy. This was something that when I gave this talk many years ago and in subsequent years when I've given it, people keep going, so what hardware do you work on? And I don't. I do this as a kind of hobby of, you know, what goes into a small Linux kernel, what goes into a small user space set, things like that. I'm intentionally avoiding, and I mentioned this in the abstract for this talk, I'm intentionally avoiding how do you boot Linux on hardware, because I don't get that. It breaks my brain, right? The whole bootloader thing. I'm starting to gradually understand how it works on x86 sort of systems, but I don't understand how it works on embedded systems, so it's kind of magic to me that my video recorder turns on, my microwave works. And I am interested, as was mentioned before, I am sort of interested in build systems. I mean, again, it's a hobby, right? Sometimes those things break and somebody wants to dive in and try and fix them, and sometimes it turns out to be me. And so the whole holistic thing of how does it all go together is sort of interesting to me, and so I tend to get into this thing of, all right, build my own kernel, work out how it goes on. All right, audience participation time. How many people have built their own Linux kernel in, say, the last 6 months? All right, this talk isn't for you people. You're probably overqualified. There are 2 other at least perfectly good talks going on outside that you may want to attend. But all right, what I want to talk about here is not how to do really, really tiny Linux distributions. It's more sort of a holistic view of what will go into a small installation if you're trying to do one, and what are the bits you need to care about, and how can you get there to try it yourself. And so if you're already perfectly comfortable with building Linux kernels and things like this, you may use the dark room to have a quiet snooze. I'm going to do this in 3 phases. We'll start at the beginning, we'll finish at the end. In the middle, there'll be another bit. But we'll start with the kernel, and like I said, I'm skipping the bootloader portion. I'm skipping the magic of how your system hands over the control to the kernel to start running. So there's a step 0, magic happens. Kernel starts running. Then we'll talk about that sort of handover from the kernel to user space, and then we'll talk a bit about what goes into the user space area. The kernel bit is where I've probably put the most concrete detail in for these slides, because that's the bit that, for me as a user space guy, is probably the most confusing when I'm futzing around with this, trying to work out how do things work. All right. The Linux kernel is big. It's a bit over 20 years old now. There's going on for 10 million lines of code in there, just in C code alone. There's 250,000 lines of assembly in multiple different architectures. These sort of numbers are pulled straight out of, I just ran David Wheeler's slot count over the kernel, over the 3.2 version, and pulled these out. And 2,300 odd directories. We will not be covering all of these today. I'll be doing an overview, not a detailed dive. But all right, it's big. It's understandable that there may be confusion around what's going on in here. So let's have a look at big to small. What is something? What sort of numbers are we talking about? Very simple metrics here. I ran, when you build the Linux kernel, you have a few options. And typically, if you're building it for yourself, you run something like make menu config or one of the GUI configs to select the options. But there are 2 or 3 useful options, for testing and fooling around purposes: make all no config, make all yes config, make random config, make all mod config is in there. I can't remember if it's spelled all mod config or all module config, but effectively these are ones that turn on options in certain default settings. Make all no config is allegedly the smallest sort of reasonable running thing. It's not the smallest you can do. You can turn on a few expert options and turn off things like you don't necessarily need print K and you don't necessarily need some of the debug options. So you can make it a little smaller, but it's a reasonable baseline. It has 200 odd things set to yes, so it's not really all no config. We suck at naming, right? It's mostly no config. It's a bit under a meg in size when it's compressed. On my laptop running make -J4, my laptop's 2-3 years old, reasonably sucky thing, but it has, it's reasonable dual core machine. Takes about 15 seconds to build this system. Not too bad. It comes with almost nothing. We'll get to a little bit in, can this thing boot usefully or not? But it has ISO-bus, it has no PCI support, for example. So, it's right there in the sweet spot for 1990s hardware. It'll come up again later. At the other end of the spectrum, we have make all yes config. 5,177 options are enabled. This takes a little longer to build. I forgot to time it, but it was well over an hour. I think it was about an hour and a half for a make -J4 on my laptop. A lot of disk activity in there, because it is traversing all 2,347 directories and building something in each of them. It has 116 things that are set to module rather than yes. These are things that apparently cannot be built as built-in, so you have to have them as modules. The comedy drivers or comedy drivers, I'm not sure which way they're pronouncing those, are a big offender here. And possibly that's a to-be-changed thing. These are, comedy build a whole bunch of data acquisition boards for lab environments and things like this, and their drivers are currently in the /drivers/staging tree, which is where drivers go to be born into the mainline kernel. There's always improvements. Anything under drivers/staging has to have a to-do file with what needs to change before it can be promoted to mainline. And so something in there is all right. There might be issues with why it can only be built as a module. I'm not sure why they don't want to be built in. But yeah, make all yes config does build everything in drivers/staging, and that seemed to be where the compiler was taking a lot of time. It was also where it was spitting out a lot of warnings, so clearly there's work to be done. But the big point here is it's 40 megabytes versus 842 kilobytes. It's bigger. Okay, so let's go back to make all no config. And here's my sort of, like I said, not a hardware guy, but I can do software and I have a laptop. I can make something work here. So my weapon of choice here is QEMU just for booting things up. And I happen to use QEMU KVM because I'm going to build for an x86 architecture just so that it runs natively and I don't grow even older waiting for things to test. I could, show off and maybe try and build something for an ARM architecture or a MIPS or something and just for fun. And that's a nice way to learn about those things. But, I'm going to have enough problems making this work. So I'll just stick to an architecture where I can understand the error messages. And so the standard way to sort of boot this up is, all right, QEMU, KVM, give it a certain amount of memory. 512 megs is sort of a reasonable amount, not too small, not too large. Minus kernel, and then you give it ... here is a path to the BZ image that I built earlier. And this is the minimal case, right? All right, it's not going to boot, but this is the smallest thing we have a chance of booting. We're running it on a simulated machine with some memory. QEMU, for those who aren't necessarily familiar with it, gives you a very basic 1990 style hardware thing. It comes with both ISO-bus and PCI bus. It has a sort of BIOS implementation in there. You can attach various devices to it, hard drives, CD-ROMs, floppies, serial ports, the whole thing. Configuration options up the wazoo, but out of the box, you basically get something nice. The nice thing is I don't have to worry about a bootloader here because I can tell it what kernel image to boot, and it sort of pretends to be the bootloader for it. Later on, we'll see I can tell it things like the Initrd image and stuff like that as well. So I save myself a lot of time for just getting something up and running at this point. All right, it didn't boot. It gets pretty far in. This is the nice thing. It actually, I get a BIOS message, it chugs along, and then we get kernel panic, and right before the kernel panic, unable to mount root file system. Well, that's not too surprising. I didn't give it a root file system. But the nice thing is it got that far. It got to the point of sort of everything works up to the point that I was stupid and didn't tell it how to do the next step. So, that's progress. At some point when you're doing this, or when you're doing any other hard problem, metaphysics here a little bit, but changing the error message is progress, because you've changed something that had an effect. Now, all right, changing the error message to "and my computer caught fire" is probably bad, but you want to change it in less drastic ways. But at least you know what you're changing has an effect at this point. Slight step to the side for a minute. The kernel itself consists of, we can probably group things into 4 or 6 or 11 different areas, and I put other at the bottom here because it starts to get silly at some point. But very roughly, you make a decision about what hardware architecture are you running your system on. Is this is it an x86 system, or is it an ARM system, or what have you? The details of how to talk now. What subsystems do I want to enable? And I'll get to some examples of this in the future, but think something like, what file systems am I going to be using? Things like this. What drivers do I want in my system? These are particular pieces of code that talk to particular pieces of hardware. So the interface between my system and the specific hardware I might be using. And other is everything else. So sort of brief examples, we have, hardware is, pick what you want. At the moment, there are 26 different architecture subdirectories under Linux/Arch. They sort of support 25 sort of different varieties of hardware. What's the other one? Audience participation time. It's not very popular these days, but it used to be very popular before virtualization was a cool thing.
User mode Linux.
Yes, user mode Linux. Booting Linux as a user space process under itself was super fun back in about 2004. You could do a lot with that. These days, it's sort of much easier, QEMU runs natively as virtualization effectively, so it's a little bit easier. User mode Linux is less popular, less trendy. And of course, some of these, ARM, for example, is this huge umbrella over many, many different systems. Similarly, with some of the other things, x86 is a directory. Underneath that, we have 32-bit, 64-bit, and the new one that I keep forgetting what they're calling it, i32 or IA32, not IA32. The one that's going to be 32-bit user space running on 64-bit address space, or vice versa. Subsystems, file systems, networking, video, for example, V4L2, video for Linux version 2. Again, we suck at naming things. But these are sort of things, and again, depending on what type of system you might be building, you might not want video. If I'm building a microwave oven or a washing machine or something like this, I probably don't need video. I might not need file systems at all. I might need, I possibly need a file system, but I maybe don't. I can build enough into the kernel for a very small single purpose usage that it possibly doesn't even need a file system. Networking, maybe I need it, maybe I don't. There are many others under there, obviously. Drivers are the easy one, right? We've all got hardware devices. Probably our system is going to need to talk to some hardware because it wants at least one of input and output. Without either of those, all right, I don't even know if it's running at this point. I can put my hands on it and feel if it's warming up maybe, but it's not very useful. So we're going to need some kind of I/O support, graphics cards, sound cards, video cards. The layer above that, like I mentioned video, the video is a subsystem. I mean, think of that as we've got hardware drivers that take the talk to the actual devices, turn them into a more neutral sort of layer, and then the subsystem layer tells us, gives us a uniform interface over that. As John's talk previous to this sort of mentioned, video is an example where it gets a bit intermixed because user space can potentially talk all the way down to systems that are actually running on the camera. So where does the layer between hardware and subsystem matter gets a little bit fuzzy and breaks my brain. So I'm not going to dive too deep into video, for example. Other is, everything else. But for example, the type of things we might have there is, do we have loadable module support in our particular kernel? What sort of binary thing can it run? Out of the box, make all no config, you can't run ELF binaries. So in that previous thing that I tried to boot that crashed without a root file system, even if I gave it a root file system, it wouldn't actually be able to run anything because it doesn't know how to run any binaries at all at this point. Darren Hart gave a talk at Embedded Linux conference in Europe last year where he sort of did a very similar split. I started writing these slides and then watched the video of his talk and thought, this looks freaky, he's giving my talk. And he actually talked about other as policies. which he didn't elaborate on this, but I suspect he could be talking about things like, what sort of cryptographic APIs we put in and things like that aren't strictly subsystems, but maybe are more overarching policies. So there's a big fuzzy area of things that don't necessarily fit as subsystems or drivers or the hardware you're running on. Okay, so let's go back to trying to boot. What's our problem? We don't have a root file system. We also didn't actually tell the kernel what to do once it had got to that point of I'm up and ready and I fall over the cliff. So we need something for it to run. This is the init process. We can go with the simplest init process known to mankind, hello world. It doesn't do anything except if it prints hello world, we know we've got somewhere else. We're changing the problem. Not even an error message anymore. We need a root file system for it to do something. Like it doesn't really need a root file system, but it likes to get that warm fuzzy feeling in the kernel that it's got a root file system. Initrd and initramfs, which I'll get into again a bit later on, is a good proxy for a file system here. This is a file that can be uncompressed, used as a RAM-based file system, and can be used for setting up the real file system later on, or as in my case, can be used as the actual file system, just sitting in RAM. I don't necessarily need a file system. So there's a sort of, by the way, at the end of these slides, I have a couple of slides of sort of resources to go and look up more information about these if you're interested. But there's a way you have to set up an initrd to make this work. You have a file, you have an executable in there, maybe a whole bunch of a file system in there, file system layout, and you have a binary that can actually run. The kernel has to know how to run the binary. It has to know how to uncompress the initrd system. It happens to be a CPIO archive. You follow the recipe, it basically works. Before we can get that far, we need to actually tell the kernel how to do this. Remember, we're starting from a make no config, 842 kilobyte binary. We need to tell it about initrd and initramfs support. This is one option, initrd/initramfs. If you also then remember to turn on the RAM block device, RAM disk block device, you get initrd support. If you don't remember to turn that on, you spend a long time wondering why that didn't work. It happens to be in the help text for initrd and initramfs, but it really should be a bit more in your face, I feel. Not that I walked into that trap at all recently. You also have to turn on ELF binary support, or again, you spend a little bit of time wondering why everything seems to be correct and your binaries aren't working. Haven't run into that one for a few years, but been there, done that, have the t-shirt. That adds about 50 kilobytes to my kernel. Not too bad, I'm still under a meg. I can make a nice little static binary. I just built something linked against glibc statically, so at this point I have another 800 kilobytes for hello world. Bit disappointing, but life goes on. Put that into the CPIO archive. Little bit of historical interest there. Okay, creating an archive, minus format equals new C. This is because there's also a format called old C. I don't think new C has been used since about, 1998 or so. Maybe a little bit earlier. It's really bad to name something new. It's just not going to be new for very long. And what happens when you do the next thing? Even newer C? We can't change this format now. We're out of names. Punt that into the root file system, and then we can try and boot. Give it the memory, give it the full path to where I built the binary, tell it, here's my root file system for initrd. Again, I'm using the fact that QEMU lets me cheat and not have a bootloader here. Normally I'd have to, this is the sort of information you give to grub2 or to Lilo or to uboot if you're in embedded LAN. And append just says on the kernel command line, put rd init equals hello. Rd init, for those who are thinking, shouldn't that be init? Rd init is just the same as init equals, except it tells it use the RAM file system as the place to get the init binary from. And if you actually run that, you build the kernel, build the binary, it actually gets to the point of it prints out hello world, and then it sits there and busy waits and uses up a full CPU. But that's success, we've made progress. So at this point, it does nothing at all except it boots to the point that I know if I gave it a real file system and I gave it real binaries, I could probably move on. So I've come to this point of I have kind of a minimal running example. I could now go in and remove things. If it stops booting, I've probably removed the wrong thing. I should put that back. If I want to add extra things, I've got my minimal example of what works. I don't have to rebuild the kernel. If I rebuild the kernel, I don't have to change that command line to test that it still works with hello world. So that's it's a useful starting point for running. So at this point, we're at the point where the kernel we can fake it out to the point of it's got a root file system, it can run a binary. I just want to quickly go over, the what happens next, because really at this point we've gone from the kernel sort of booted, whatever that means, and is ready to hand over control to something that comes next. In normal world, desktop user space, server space, what tends to happen next is the kernel, an Initrd might run. I'll talk about systems that have an Initrd support, and then we'll talk about why you might not need them. So an Initrd is, like I said, this particular structure of file that gets uncompressed, basically looks like a file system in RAM for the kernel's purposes. Everything it needs to run is built into the kernel, or is available immediately and guaranteed to be available as a module or whatever. It doesn't need to do any special logic, it can just run. The idea then is an Initrd will, this file system will then do whatever examination it needs to look at the system to work out what else do I need to load to be able to boot properly. For example, do I need to mount some NFS devices? Do I need to connect up a particular funky piece of network hardware? Do I need to wait for some USB devices to be available? Things that are not necessarily going to be there immediately, an Initrd can organize and work out what's going on. This enables companies like Debian and Ubuntu and Red Hat to ship one kernel that pretty much runs on all of our hardware. They're shipping one kernel with a reasonably rocket science level Initrd and a lot of modules, and it works out, it does sort of hardware detection on your system and works out what modules do I need to load, where did you tell me your file system wanted to be, your root file system, your home file system, and so on. By way of example, the latest Fedora kernel has something like 2,200 modules in it. I don't need to have all of those loaded on my laptop, but between the conglomeration of all of us in our room here and all the hardware we might run it on, probably most of them get exercised. Although it would be interesting to see stats about which ones don't get used very often. When an Initrd has finished sort of setting everything up and is ready to hand over control to the real system, there's I don't know if we want to call it a function call or binary or whatever, there's an entry point called pivot root, which is kind of funky. It basically, it does the two-card Monty trick of saying, all right, I've got the root file system here, now replace me with the real root file system and hand over control to that. And it moves the Initrd file system actually to dev RAM 0 or dev RAM or something, depending on how the system's set up. So you can access it later if you want to, but typically at that point it's saying you're all set up, I'll get out of the way now and just keep running it. It's kind of like exec in shell or exec in a C program. Replace myself with the real root file system. Pivot root means, and change the slash, because at this point it's sort of loaded the real root in under a particular point so that it can mount it there, and then it says, all right, pivot the whole directory tree so that slash is now that real root and hand over control to that. That's where the name comes from. And then at some point some startup scripts will typically execute. The control will be handed over to the actual binary init or telinit or what have you, and it will run something, maybe system5 style scripts, maybe upstart style scripts, maybe systemd, maybe something entirely different. These are, I say at the top, one or more of these things could happen. There's no reason to necessarily run specific startup scripts. This is common in your desktop and server environments, but if you're doing a tiny little embedded device like home environmental controller or something like that, you know exactly what needs to run on the system. You can just start it all up possibly as one single binary. Systemd is getting us a long way towards making that, what's the word I'm after here? More sort of uniform. You maybe don't need to write your own custom binary to just start up the things you do. You can do systemd, tweak the configuration of systemd down to very, very minimal, and it will just work, because the idea is it's one binary. It's not starting a whole bunch of system5 scripts. Before you get there, you kind of have to sit a graduate level exam in how to set up systemd and configure it and all that sort of stuff. So there may be a learning curve. It may look like that, but when you get to the top, it's apparently a really good view. So there's, it'll be interesting in a couple of years how that all shakes out, because systemd is fairly new at the moment. A lot of sysadmins are wrestling with it, including myself. It's a whole new vocabulary. What will the upstart story be like in a few years? Things like that. Okay, so that's the, sorry, back here I said I'd talk about what happens. You don't necessarily need a Initrd or a initramfs. A initramfs, by the way, is a slightly different structure to a Initrd, but serves exactly the same purpose. Think of them for this purpose of this level talk of being the same thing, more or less. if you already know what your system needs to do, if you know the hardware is not going to change, if you know I don't have to do introspection to work out what really goes on in the system, you don't need to do the RAM file system and the pivot route and everything like that. You might just want to load up your real stuff and go with it. You don't need module support maybe, you can build in the file system, stuff like that. So there's no not necessarily compulsory that you're going to have an Initrd or pivot route or things like that. But most systems these days you get in distributions will have them because they need to run on many different pieces of hardware. All right, the fun side of things. But this is where it gets much harder because I can't really tell, I could talk to a particular style of system that you might be wanting to build, but I don't want to, I'm trying to give a bit of an overview here and make this a little bit, I don't want to say too inspirational, that sets the bar too high for me, but give people an idea of here's how to investigate this on your own and play around. It's fun stuff. And the question would be, why are you building a small Linux installation? It could be just for education purposes. Small installations are probably easier to build than large installations. Start small, work large. You could be trying to build something that runs on a tiny embedded device. This is the Embedded Linux conference videos that I talked about are really good value to watch, even for someone like me who's a complete idiot and not very good at embedded hardware, because they're always working with really cool hardware. And so you get to see, Linux actually running on useful stuff, not just the finished product. You might be trying to build a sort of Swiss Army USB stick, something as a sysadmin you carry around in your pocket that will boot on all the systems in your machine room or in your desktop environment as your rescue device, right? So it needs to have various Windows file system support built in so that you can mount those and see what's going on. It maybe needs to have a couple of different funky pieces of network negotiation tools on there, something like that. Examples of these in the real world are Damn Small Linux, Puppy Linux, things like this. There's probably about 73 others, but they're the sort of two that fit on things like USB business card or USB stick or single floppy device back in the day. You might be trying to build a system that targets very tiny memory use. I mean, here the next three are the sort of the triangle of trade-offs. You probably can't get all three very easily. Do you want it to use maybe not very much space when it's running? So you're targeting things that are very memory, very resource unintensive or can unload themselves quickly, things like that. Android phones are a sort of example of this, right? You don't have infinite amount of memory in your phone. You have things that are running for a very long time. They probably shouldn't eat up memory, even when they're running for a long time. Do you want tiny storage usage because you've got something that's maybe a fairly useful processor but doesn't have a lot of memory in there, or the memory can get corrupted very easily because it's in imagine you're building a device that needs to go into a fairly hardened environment. Memory is something that might break very easily or be slow. So if you can cut down the memory usage, your device will appear more responsive and you won't have to go up to the space station to replace the RAM chips or something like that. I mean, that's obviously a ridiculous example, but hardened environments are a case where memory is fragile. Do you want fast power on to the point where the user can use it? Home environment system is a good example here, where I know there's at least one around that runs Linux. And a person walks into their home, they want to be able to push the button and have the GUI come up within a couple of seconds. Like a couple of seconds is a reasonable period of time, because you go push the button, by the time you bring your arm back, you've already lost a second. It's only another second till it blinks into view. 10 or 15 seconds really kind of sucks from the user perspective there, because like, is it on? Is it on? Hello, hello, are we on? And 10 seconds is an eternity in that point of view. And in that case, if you're going for fast power on, you probably want reasonably fast memory. You want to be able to put a lot of stuff in memory so you're not fetching it from your slow permanent storage. If it's an embedded device, your permanent storage is not going to be necessarily a very fast SSD disk. It's going to be something like a flash chip or something that's a little bit slower to read from. So yeah, that's your trade-off there. I'm not going to pick a system that's right for you because obviously they vary on requirements. But each one comes with trade-offs and needs. Which is a very long way of saying the next bit of the talk, the next bit of the talk gets a little bit fuzzier in terms of specifics, but I want to give you some ideas of the type of things you want to look at. So we're going to run something. Presumably we've got to this point in my example where it runs Hello World, which is exciting, and possibly I get a 15-minute talk out of it somewhere, but it doesn't actually do anything. And so you want to run something, so you're going to need some binaries you're going to run. The question is, how do you set up this? If you're doing a system that is anything more than single purpose, and if it's truly single purpose, I'm not sure Linux may be overkill for what you're doing, you're probably going to run multiple binaries. They're going to have some common code in. Do you really want to build all of them as static binaries? Maybe you want to have shared libraries in your system so you can share things, so you can upgrade easily, think of the future of your product. Even an embedded product gets upgraded as time goes on. New versions, new hardware. Over the prototype development release sort of phase, you'll do upgrades. Or do you do something like the one large binary that has multiple purposes, because at that point you don't need to worry about, you can build this big static thing that you dump on the disk and it does everything. So the one large binary approach, the sort of common one that most people have heard of is Busybox. A little bit of history for those for whom it's maybe just a word rather than something they've used. I mean, you've all used it, maybe without realizing it, but this was written by Bruce Perens back in 1995 or 96, pretty sure 95. Largely for projects like Debian and things like this, where you want to have something that fits on a single floppy disk that can support all the things you might need, a useful thing. It rapidly became useful and for some values of complete. It's still actively maintained and actively used in embedded devices. The idea is this is a single binary that either takes parameters on the command line, so you call Busybox and pass it ls, and it runs as ls. But if you actually call it if you rename the file to be ls, or you symlink it more productively, it looks at what its name is and goes, oh, I'm being called and my name is ls, so I should act like ls, or I should act like CP, or I should act like DD. Busybox itself has 100 and who knows what different utilities in there, shells, networking tools. You can pretty much build up an entire user space very, very similar to what you have on a desktop from Busybox stuff. The shell's the shell is not bash, it's smaller. So you notice a few bashisms won't necessarily work. You notice a few things like PS doesn't have the 6 billion options that GNU PS has, because GNU PS is carrying around all the sys5 things, plus all the BSD things, plus all the who knows what options, and they just stick with the POSIX versions of things. But you get a lot of options about what you build into Busybox, what you build out of it. You can make it tiny, you can make it huge. It's a very nice compilation environment, very familiar to anyone who builds a kernel, because they've actually taken the kernel build system and reused it. And is actively used by people doing embedded devices. So it's also very nice code to read. A little bit twist your brain into pretzels type of code in places, because they do try and save bytes. But it's fairly solid, fairly well used. Useful to play around with too. I mean, you can build Busybox in your home directory, or in a temporary directory somewhere, statically link it, and just mess around with it. I mean, you can literally call it, as skipping ahead to the bottom of this slide for a minute, I mean, you can literally just call it like that. And it's fun to sort of run Busybox, the Busybox shell, for example, ash or hash. It comes with multiple shells, in fact. And just see, what's life like in there. So testing this type of thing, you don't have to build your own tiny kernel and run it inside QEMU and things like this to test user space environments. You can actually do a lot of the testing on its own. And just at the end, I'll touch on this again. It's not too big. I mean, I built, a couple of days ago, I built the latest Busybox Git repository checkout, except I had to turn off networking. There was some build problem there, and I couldn't be bothered messing around trying to work out what was going on with the build thing. When I try and build it statically, it's basically 2 megabytes. Networking would add another 10% to that, so call it 2.2, 2.3 megabytes. That's one binary that gave me 120 something utilities there. I could run most useful things that didn't require X right there. Throw that in with my 1 megabyte Linux kernel, and I've got less than 4 megabytes, something that's actually useful. At some point, as life goes on, you're going to need a C library. You're going to get sick of building things statically. You then have to make another choice about, again, what are you going for? Power, convenience, space, maintainability, friendly community. Many things get traded off here. glibc is kind of let's call that the default standard. It's also very big, it's very cumbersome, it's very hard to build a customized version of that. It's a little bit precious in its build system and wants to be built in certain environments. If you want to build it in a much more constrained environment, you're probably going to use some very nasty swear words at points. It's a learning experience, let's put it that way. eglibc is a sort of acknowledged fork of glibc that is, the E stands for embedded. But their goal is basically to track glibc, make it easier to turn off portions that you might not need. If you're building an embedded device, you might not need all the NIS support, you might not need the NLS support, natural language support, you might not need who knows what, right? There's various big chunks of glibc you can carve off. They've also worked pretty hard on making it build more nicely on alternative architectures. One of their goals is try and be they say a welcoming community. Implicit in that is there are non-welcoming communities building C libraries, which is true. glibc community is a little bit like the Linux kernel community, asbestos underwear required occasionally. UClibc is an alternative approach to this whole thing of trying to build a POSIX-compatible C library that is very small. The U here is a ASCII replacement for mu, micro. Been around for many, many years, typically maintained and worked on by many of the same people who work on Busybox with many of the same goals. It used to have a reasonable competitor called DietLibc, which doesn't seem to really have been maintained very much in the last 4 or 5 years at least. Now, the difference here is, if I was going to pick one of these, the question is, do you want to rebuild all of your stuff or not? UClibc aims to be source code compatible with glibc as much as possible. glibc makes a few assumptions, but by and large, UClibc says if your code builds against glibc, it probably builds against UClibc. EGlibc aims to be binary compatible as well in terms of the structures it's using internally and things like that. So the idea is you could probably build something against where it's fully shared glibc and place it against EGlibc, and it more or less just works without having to rebuild your entire stack of software. If you're building an embedded device, UClibc is not such a sacrifice then because you're going to be rebuilding the whole thing anyway, and it's meant to be small. It won't take very long. If you're doing your desktop, you're probably not going to build it around UClibc because you'll be rebuilding for a week. And making things build against UClibc, like I said, mostly works. Every now and again, you have to work out what's going on. UClibc has a few more options that EGlibc doesn't necessarily quickly expose for embedded devices, things like running on devices that don't have an MMU device, don't have various other sort of shared memory features that exist in all modern CPUs, but in tiny little embedded ones, maybe not so much. So there's pick your particular dessert there. That's something to play around with small versus power versus convenience. As you move forward, you're going to run into other bits of the kernel that exist on your desktop but don't yet exist in your tiny little experimental distribution. procfs, this is the thing that /broc lives under. All the information about process management. Various binaries start to assume this thing exists. And so at some point, you're just not going to make progress until you add procfs. sysfs, which has the /sys directory for various system-related things. You're going to eventually want to start using binaries that assume that's here. tempfs crops up now and again in sort of unpredictable fashion. udev is going to rapidly enter your world if you're wanting to build something that runs on real hardware because it's the way we do device management a lot these days. That sucks in tempfs, and that sucks in you have to make a C library choice there, and there might be swearing involved to build it, but it basically is not too bad. C groups have broken my brain lately. I don't really understand them enough yet. I understand that when I type mount on my desktop, it's a lot longer than it used to be. It goes on for screens now. It used to have like 4 entries in it. This is because C groups appear as mounted devices. I'm still working out that. I was somewhat encouraged to hear John Corbett say in his previous talk that everyone else who's a lot smarter than me is still trying to work that out as well. So maybe there's hope there, or maybe they'll give a talk later and explain it. But those are the type of areas that the educational experience will kick in, and you'll have to work out, do you need them? What do you need there? They're all buildable, they're all pretty easy, but there's education, except for C groups. They broke my brain. Finally, build environments for these sort of things. If you're trying to build something like you build your own kernel, build your own user space, things like that, you're effectively cross-compiling. Even if you're doing what I'm doing, which is running an x86 laptop and building on x86, building an x86 sort of jailed system like this, you're still wanting a compiler that knows to talk to that C library over there that's running in my embedded environment rather than the C library on my main system. This turns out to be a lot harder when you're doing x86 inside x86 than if you're doing, say, ARM inside x86. Because ARM inside x86, things break very early when they start trying to pull things in from your normal system because it's not an ARM environment. And so you're building a cross-compiler and things fail immediately. With x86, it'll just quietly link against your glibc on your system, and then you'll be running your QEMU environment and it'll all fall over. This happens a lot. There's a project around called BuildRoot that sort of specializes in scripts to help you set these up. And Again, because I do this for fun, I don't really want to run build root because my salary doesn't depend on making this work. I want to understand it. But pulling build root apart to work out how it works is very useful. You end up having to build a compiler, build a bin utils so that you can do useful stuff with this, build a C library. Typically this goes build compiler, build C library, sort of, build bin utils against that C library, go back and rebuild C library because now it has the full bin utils to build itself, have a cup of coffee, test this thing, rinse, wash, repeat a lot of times. It's a little bit fun, but you get that. And like I said, x86 inside x86 is tricky because you don't know when it's not quite working. Finally, and this is more for believe this slide exists and the next one, and look at the version online that they'll put up on the conference website. Useful things if you're interested in going further here. Rob Landley, who does various bits of embedded work, has a lot of nice talks up where he's talked about things like cross-compiling ARM devices inside QEMU and using things like Ccache and distcc to build things a bit faster if you're not just building on x86 systems, because it can be very slow to run emulated systems inside QEMU. One example of many from IBM's developer works talking about Initrd and things like this. I found that site to be quite useful over the years for holistic sort of, more advanced maybe than I'm giving here with more details, and always to be checked against reality because something from 2006 is going to have changed slightly in 2012, but it gives you the big picture. Linux hasn't changed that much. Embedded Linux conference, which I mentioned before. Their videos are online at least for the last couple of years and are excellent. It's worth sort of downloading a few and watching them. Very interesting, very entertaining speakers. Lots of accents, so you have to listen carefully, but you know, they speak French better than I do. Pull apart your favorite distro's installation sequence, like, you know, Anaconda on Red Hat or Deb Bootstrap, things like this. See how it works. That's always fun. Daniel Barangers is someone from Red Hat, I think, who works on Linux containers, LXC, works on libvirt, things like this. Just coincidentally, after I'd written these slides, re-enters lwn.net on the front page today for having announced libvirt shell for setting these things up. Linux containers are a good way to sort of kind of think like chroot on steroids to some extent. It's a case again where you want to play around with maybe your own self-contained user space to some extent without having to build your own kernel and things like that. Finally, the Busybox and UC-libc mailing lists are a good place to look at for, you know, they're just interesting to read because they give you ideas of the type of things you can do. More importantly, the type of things other people are doing. So it sort of stimulates the brain. Okay.
We have time for questions. And here you said that everyone would be falling asleep and there'd be no questions.
Yeah, well, that didn't work, did it?
We're even now.
Any opinion on MDebian?
No. So the question was anything on MDebian. I have to unfortunately fall back on the, I do this for fun, so I'm not really looking at too much at what distros are doing with embedded stuff and things like this. Also, I just tend not to have played around the Debian world very much, so it's on my long-term list of something to look at, but I must admit I haven't got there yet. I do this for fun very, very slowly. It can take me a year to get to my next bullet point.
Further questions? Please come down the front if you do have a question.
So you mentioned UDEV and virtualization. Did you have fun with Ethernet cards and MAC addresses or anything like that?
In what sense? Sorry?
So with UDEV, when you get a new MAC address, in some virtual environments, you'll get a randomly generated MAC address.
Right.
UDEV will create you a new Ethernet device, or at least an interface each time.
Yeah, so the thing is when you're running in a virtual environment, and particularly when you're setting them up, UDEV allows you to do persistent naming of devices based on identifying features like MAC addresses for Ethernet cards. And the question is sort of, I think he's setting me up for fall here, did I have fun with Ethernet cards? I don't think he meant fun. The nice thing is this is kind of a solved problem in the, at least in the x86 sort of QEMU space, because Virtua and the sort of the libvirt project has sort of solved this with their, they provide an overarching API style interface to QEMU, to KAVM, to VirtualBox, to a few others. So you can sort of have one interface for running all of your virtualization needs for some value of works. And the nice thing there is when they set up new machines, you can create new machines through them, and they actually give it, you can either specify the MAC address or they can give you predictable MAC addresses. What does tend to happen is they'll give you MAC addresses with a particular prefix for your new devices. So the question was, in the sense of, this was very difficult certainly a few years ago. I feel it's become easier in the last couple of years because those virtual setup systems have made it easier to get predictable MAC addresses. Typically the problem is when you clone a device, if you've got a virtual system working and you clone it, it will often create a new Ethernet interface in addition to the one that was already there, and so now you start them both up and you've got either two Ethernet interfaces with the same MAC address, which is annoying, or the new one with a completely unknown MAC address which doesn't come up at all. Neither of those cases are ideal. You have to do a little bit of shell scripting to script around that when you're cloning devices. I must say, it's annoying, but it is what it is. I don't know of a neat way around that yet, and the smart people who work in this area haven't come up with one yet either, so it's, you learn to work around it. Yes. Yes, but you have to. You have a single Ethernet interface. Yes, so he's saying if you've got a single Ethernet interface in your device, you can basically blow away the config file and it won't go creating new things for you. But it is something you have to be aware of for sure, and it's solvable.
So you seem to be testing some funny corner cases of the kernel build system. I didn't even know all no-config existed. But have you looked at the config files that actually define dependencies? Because you mentioned a problem where you were trying to build kernel that supported init RAM disk, but it needed the RAM disk block device support. Really, if you try and select, or even if the menu config shows one option that should depend on another option, there should be a dependency in the K-config. So that's almost a bug in the build system.
No, it's actually not a bug.
Is it not a bug?
Sorry, I should have been clear about that one. So when you're selecting the configuration option, there's a config option called initrd/initramfs support, and you enable that. And then if you actually read the help, and the config file does it correctly, it says if you want initRD support, you also have to enable, if block RAM dev is enabled, you will get initRD support. So it's not, because the option is serving two masters here, like it's certainly a wart in the way the config system is set up. That you probably want two separate options there, because you turn on this thing saying it gives me the capability to have both of those, but I also have to remember to turn on this other thing. And to be fair, it's documented in the help. It's not too hard to go down and find where the block devices are, turn on RAM disk support. There's a lot of block devices that takes a little bit of messing around to find it. But, so it's not really a bug so much as a bit of a usability wart. And I only sort of mentioned it here because, again, it was something I bumped into earlier last year. At some point, I spent a long while trying to remember, wait, I've got this to work all the times before. How am I not getting an initRD to work?
It still seems to be a dependency problem, though.
Well, the dependency, I don't know. Yeah, I mean, it depends what you expect that option to do. The option is, it's one of the things you need to enable for this to happen. There's no turn on a initRD support button, is probably the slight wart there.
Yep.
Any further questions? If not, can we put our hands together and thank Malcolm for these adventures in building a small Linux installation. I also have a courtesy of Linux Conference Australia 2012, a little gift for you, being a glass penguin with gold plating. There you go. I also would wonder if people would care to put their hands together and thank the AV team up the back and the two little boxes up there, Andre and Steve, because they've done a good job this afternoon.